Okay, this is the second lecture here with respect to applications associated with Faraday's law. This specific lecture has to do with transformers. So with respect to transformers, first of all, make sure that you watch the transformer demonstration video first that I've put for you in the folder on Schoology. So go ahead and pause the lecture now to look at that video. Okay, now that you've seen that demonstration, here's basically what you saw. Okay, so first of all, I had my primary coil, my first solenoid, this guy here that I had plugged into the wall socket. I'm not going to do that again here. But right here is what's called the primary coil. Like so, and then over here is a generator of some sort. This is me plugging it into the wall socket such that an alternating current flows. Let's say that the voltage within the primary, and I'm not going to use the RMS notation here. Let's say that the voltage within the primary is just referred to as V sub P, and then at this moment that we're looking at it, the current is flowing in this direction like so, with a value of I sub P. There are a number of turns here associated with the primary that's labeled as N sub P. Now at this moment, as the current flows, let's say it's flowing in this direction like so, so then therefore there is a dipole magnetic field that is produced by that current, and that dipole magnetic field is such that the north pole of it is here at the top of the diagram and the south pole is here. So then therefore roughly looks something like this. Let me get a new red marker here, please. Okay, here we go. And I'm just going to draw a couple of magnetic field lines, like so. So here's that magnetic field B. Right here is a north pole. Right here is a south pole. Okay, and then I had my secondary coil of wire. That was this ring, for example, here that I used in the demonstration, or alternatively the second solenoid that had the light bulb attached to it. So this is referred to as the secondary coil. And I'm going to go ahead and draw that right here. Like so. And the secondary coil has a number of turns associated. This is written as N sub S. Okay, now as this alternating current here changes with respect to time, this magnetic field here changes with respect to time. What it literally does is it oscillates like so, 60 times per second. And then as it does oscillate, it's basically changing its magnetic polarity as time goes on. So then therefore a moment later then, this would be a south magnetic pole up here, and this would be a north magnetic pole down here as the current flows through the primary. So then therefore, to make a long story short, what you end up with right here is a changing magnetic flux through the secondary that then induces a voltage in the secondary. The voltage that's induced in the secondary is referred to as V sub S. Okay, now from Faraday's law, that induced voltage is the following. This expression here, where this is the changing magnetic flux through the secondary as a function of time. This right here is the number of turns that is flowing within the secondary. Okay, now the induced current. The induced current always has to flow such that it opposes the changing magnetic flux. So to make a long story short, what that then means is that the alternating current that's induced within the secondary coil is always in the opposite direction of that of the primary. So if the primary's current is flowing like so at this moment, then the secondary's current has to be flowing like so at this moment. That would then point, for example, down here on the diagram like so, and up here on the diagram like so. Notice that it's opposite of what I'm drawing here for the primary current, like so, okay? Okay, now here's where it gets a little tricky. Because this right here is an alternating current, that's then going to induce a voltage in the primary as well, because there's a magnetic field associated with this alternating current. And incidentally, by the way, at the moment that I've drawn this diagram, I'm not going to draw this guy's magnetic field at this moment, but notice where the north pole of that magnetic field would be. If this current was flowing like so, then the north magnetic pole would be down here at the bottom. That's basically what the ring was doing when you saw it being repelled by the primary. The north pole that is generated down here by the secondary's magnetic field is pushing against this north magnetic pole here. So as this reverses polarity 60 times per second, this will reverse polarity 60 times per second and will always be in the opposite orientation of that of the primary. So it's like you always have a north pole and a north pole repelling each other, or a south pole and a south pole repelling each other, and the reversals of polarity occur within each coil literally 60 times per second. That's why you always saw the secondary coil here being repelled by the primary. And then in the second demonstration that I did, I used a secondary solenoid and I had a light bulb hooked up to it just to show that there was a current flowing within that secondary. The current is flowing here as well, of course, but there's no light bulb being used in that portion of the demonstration. Okay, now, as I said, here's where it gets a little tricky. Let me now draw the following diagram. Okay, so here's the secondary, for example, like so at this moment that we're looking at it. And the current flows like this, and then you have a dipole magnetic field associated with this. Once again, let me just draw a couple of field lines like so. Okay, but the polarity of this magnetic field here, remember, is opposite of that of the primary. So then therefore the field lines, the directions associated with them look like this. Let me clean this up a little bit. Like so, where right here is a north magnetic pole and right here is a south magnetic pole. As I said earlier, this north magnetic pole is pushing up against that north magnetic pole in my ring demonstration. Okay, now, right here is the primary, like so. And then because we have here a changing magnetic flux passing through the primary, then the voltage is induced within the primary. The voltage that's induced within the primary from Faraday's law is the following expression. This voltage is the same as this voltage. As long as we make the following assumption, we assume that there is no heat loss due to resistance. If there is no heat loss due to resistance, then the generator's purpose is basically to get this initial current flowing. Once this initial current is flowing, that then induces the current here in the secondary, which then induces the current once again in the primary, in the opposite direction always of what you see here in the other coil. So basically the generator, it like starts an oscillation, and then as long as there is no damping, as long as there is no heat loss due to resistance in this case, then that oscillation will essentially occur forever. So the alternating current here induces an alternating current here, which induces an alternating current here, which induces an alternating current here, and so on and so on and so on, as long as there is no heat loss due to resistance. Now, of course, there is heat loss due to resistance, so then therefore the process has to be given a push every now and then, if you will, by the generator. It supplies the energy necessary to sustain the transformation. Okay, now also notice that I wrote down here the changing magnetic flux through the primary as being the same as the changing magnetic flux through the secondary. If the two values were different from each other for complicated reasons, that would ultimately violate conservation of energy. I end up now with a transformation equation. The transformation equation is to take the top expression and this expression here and write each of them in terms of the changing magnetic flux with respect to time. When you do, you end up with the following expression. Voltage in the primary divided by the number of turns in the primary equals then at the top voltage in the secondary divided by the number of turns in the secondary. It's specifically this expression here that allows you to change voltages. You can change voltage from one value to another by adjusting the number of turns within the individual coils of wire. If you set up a situation where you increase the voltage from one value to another, that's referred to as a step-up transformer. If you set up a situation where you decrease the voltage from one value to the other, that's referred to as a step-down transformer. Okay, now as I've been saying throughout this description, we're assuming that there is no heat loss. So then therefore, if there is no heat loss, the power that is delivered to the primary is ultimately the same then therefore as the power that is delivered to the secondary. Remember that power delivered is I times V. So then therefore in the primary, the power delivered would be this expression here, and that's equal to the power delivered to the secondary, once again assuming no heat loss. I times V. like so. Now you do need to know these two expressions here, so commit them to memory. They're not given on the actual AP exam itself, but should you encounter a problem on the AP exam involving a step-up or step-down transformer, it's going to be nothing more than plug and chug. Basically, does the student know what the formula is? So then therefore, I'm going to do an application of a step-up and a step-down transformer situation for you in the second of today's lecture examples. So go ahead and copy down that example now, please. And incidentally, by the way, I will also post for you in the folder a short screencast taken from a different Mechanical Universe episode than the one that you watched that shows the alternating currents here within a transformer from the primary to the secondary. That will be put into the folder as well. Make sure that you watch that screencast. Okay, so here is that application problem. This is once again the second of today's lecture examples. What we're doing is we're generating at a power plant 120,000 watts. So P is given to us as 120 kilowatts, that's 120,000 watts. Okay, and then we transmit this power through the electrical grid out to the city, for example, through what are called transmission lines. You want to make sure that the resistance in those lines is as low as possible. We're given the resistance in those lines is 0.4 ohms. Okay, now in part A of the problem, what we're going to do is transmit the power in an extremely low voltage, 240 volts. This is quite frankly very inefficient, as you'll see. All right, so now let's say we transmit at just 240 volts. So it's like the slope of our pinball machine, if you will, is extremely slight. Therefore, in order to deliver this much power, this will then require a huge amount of current. So P is equal to IV. Let's just go ahead and calculate I. That's P over V. So it's 120,000 divided by 240. So 120,000 divided by 240. And this comes out to be 500 amps, which is a huge amount. And then, therefore, because we're transmitting this through lines that have a resistance of 0.4 ohms, there's going to be a huge amount of power loss as heat. So the power loss as heat is I squared R. So take 500 and square that and then multiply it by 0.4 ohms, and you end up here with 100,000 watts. So you generate 120,000 watts of power, but you'll lose 100,000 watts of it due to resistance. That's obviously a very inefficient situation. So what is the percentage lost as heat? Well, the percentage lost as heat is 100,000 divided by 120,000, and then I'll multiply by 100 in order to convert it into a percentage. So doing the math here, and this comes out to be 83%, which is obviously extremely inefficient. Therefore, instead of transmitting the power at a low voltage, what we then do right at the power station itself is we then immediately use a transformer to step up the voltage to an extremely high value. In part B of the problem, in this case, it's 24,000 volts. All right, so we use a step-up transformer to basically take the pinball machine and tilt it at an extremely big angle. That's a nice, easy way of thinking of it. Therefore, the amount of current that has to flow to generate all of this power is relatively small. So let's go ahead and calculate now the current I, that's P over V. So this is going to be 120,000 watts divided by 24,000 volts. So 120 divided by 24, and this comes out to only be 5 amps. Therefore, the power loss here now, I squared R, as you'll see, is not much. So 5 squared, and then multiply that by 0.4 ohms, and this turns out to only be 10 watts, which is next to nothing in terms of the original 120,000 watts that you're generating. So this is very nearly 100% efficient when you then transmit at extremely high voltages. So the basic idea behind power transmission is as follows. You first of all, of course, generate the power at the station, and then you immediately step up the voltage to extremely high values to transmit it out to the electrical grid. But then you want to step down the voltages by using more transformers. They usually do these in stages, as what are referred to as transformer substations. There is, for example, a transformer substation that you may have driven past on Lincoln Boulevard. There's actually a couple of them. There's one on Lincoln Boulevard in Santa Monica, and there's another one at the corner of Lincoln Boulevard in Fiji in Marina del Rey. Those are step-down transformer stations. So what they then do is they repeatedly step down the voltages by using these transformer substations, and then they eventually send that out then to the city. They eventually send that out, for example, to the city streets and the residential streets as well. The last step of stepping down the voltages to low values that you would then get in your home, 120 volts as the VRMS. That last step is a step-down transformer that is housed in a gray cylinder that you may have seen, for example, mounted on an electrical pole right next to your house. That's the last step-down transformer prior to the power being directly delivered to your home. Okay, let me go ahead and pause this here as part 2 of today's lectures.